All right. Good morning, everybody. Today we'll continue our discussion about module number 3. Hopefully definitely matatapos natin siya this week. I'm just not sure if we'll be able to start a brand new module on Friday. So kaya hindi ko pa na-upload yung module number 4. But let's see, let's take our time because it seems na medyo 1 week pa lang naman tayong delayed. Hindi ko kasi na-foresee yung haba ng mga discussions na gagawin natin for these methods. It seems that putting one method in two methods in one meeting is a bit ambitious for me. So hindi ko siya kinakayang i-cover. So kaya medyo maraming topics dun sa modules 1 and 2, but hopefully in succeeding modules we'll adjust a little bit. And don't worry because the semester meron pang 2 weeks yung semester na hindi napasama dun sa timetable natin. So I'll just be eating some of those buffer weeks. Pero hindi na ako magdadagdag ng topics nor ng laboratory exercises. All right? So last time, oh by the way, guys, how was the exercise? Nagdalian ba kayo or nahirapan dun sa last exercise? It seems that at least the D2L and D1L students ay wala masyadong tanong last time. Medyo nahirapan lang sila sa pagsisave nung previous values ng C and B for the Anderson-Bjork algorithm for the regular falsy method. But other than that, I think they were good. Yun lang actually yung tanong. All right. So how about the others from D3L? Kumusta yung lab exer? Or even those D1L and D2L, do you want to say something about the exercise? Or so far, so good? Okay lang naman? Masyado bang madali?
Sir.
Yes, CK?
Yung sa time po, kailangan po ba talaga yun ilagay?
Hindi na siya kailangan. As I mentioned last time, lalo na kung nag-excel kayo, syempre yung pagdadrag, hindi nyo naman siya matatime, right? So, I think I mentioned it last time na hindi na required ilagay yung time. Gusto ko sanang i-compare yung time it took for the iterations to run. Pero mas mabilis pa rin kasi yung yung regular yung Newton-Raphson kaysa dun sa mangyayari sa secant method. So hindi ko may illustrate yung gusto kong ipakita. And yeah, I understand that some of you are using Excel. So hindi na lang kasama yung time. I also mentioned this to your lab instructors na pag-check wala ng points yung time spent for running the algorithms. Okay?
Sige po, sir. Salamat po. Hindi po ako umattend kasi nung last class.
All right. No problem, CK. Okay. Hopefully nabanggit ko, sana I'm not mistaken. So yeah. And then Leon Grace said, okay lang naman. Dun sa Anderson Bjork, mahirap mag-code. Okay. Now, there are some D2L students kasi na-checkan ko na yung lab exer nila. Just be careful in writing the code. I know that you know the process, and if I will ask you to explain it to me verbally or in as a written narrative, kaya nyo. Pero pag kinoding nyo, kailangan nyo maging medyo careful kasi meron sigurong ilan na nagkamali lang yung lagay ng isang line, nauna siya kesa dun sa isang line. So that's why their entire code crumbled. So hindi nabigay yung intended output. So if you guys are the thing is read the comments that we give on your laboratory exercises so that hindi nyo na siya mauulit or hindi nyo na siya ma-repeat sa susunod na laboratory exercise. Okay? So take note of that. Okay? And then I'll be uploading the answer key probably meron pa kasing 6 na hindi nagsasubmit or 5. So I'll probably upload it siguro later tonight or tomorrow, okay, for you to see yung nasa 1.8. Okay. And then hold on. Excuse me guys. All right, and then today we'll finish up or we'll wrap up our discussion about the Newton-Raphson method. Okay. Now, what are the key takeaways that we had with the Newton-Raphson method last time? Well, for the Newton-Raphson, this converges fast, right? Because it converges quadratically. Okay? Ang problema lang kay Newton-Raphson is it will converge quadratically only if we choose the initial guess to be close enough to the actual root that we're looking for, right? So if x of 0 is close enough to uh, to the actual root r. And I think we gave an estimate kung gaano siya dapat kalapit because the Newton-Raphson theorem tells us na sa kahit na anong sa sa kahit na anong function, as long as some generic conditions were met, okay? Sa Newton-Raphson method, lagi kang may mahanap na interval or neighborhood nung neighborhood around the root r such that if you choose your initial condition to belong to that neighborhood, then the Newton-Raphson will converge quadratically. All right? Ang problema, hindi natin masasabi lagi na close enough yung x sub 0 natin kay r. Now, sinasabi niya lang laging merong small enough interval kung saan pwede kang pumili ng kahit anong x sub 0. But the convergence is not guaranteed like what we noticed with the bisection and the regular falsy methods na lagi sila nagko-converge. Sa Newton-Raphson, hindi. Okay? So I think last time we have seen let's see, that the distance between the initial guess and r should be the reciprocal of 1 over the reciprocal of m. M is basically this constant. All right? So titingnan natin yung ratio nung first and second derivatives scaled by 1/2 or negative 1/2. Tapos ganun, yun yung magdedetermine dapat, gaano dapat kalapit yung initial guess kay R. But the thing there is the payout is good kasi napakabilis nung convergence. Quadratic yung convergence niya. All right? Okay. Now, yun yung hindi yun yung maganda about Newton-Raphson. Though yun din yung misgiving niya, right? Yun din yung cons kay Newton-Raphson. Mabilis siya pero hindi siya laging nagko-converge, right? Now, if it converged, then the next thing we want to know is how close is the solution that we got to the actual root. Sorry guys, kung kailan yung klase natin saka sumusumpong yung allergy ko. Hold on. Ito yung problema ko. So pag nagsimula yung allergy ko, nagbumahin ako or nag-sneeze ako once, sunod-sunod to. So kaya ko mag-sneeze dire-diretso ng 30 minutes to 1 hour. So kailangan ko siyang pigilin. So kailangan ko mag-pause from time to time pag mag-sneeze na ako. So sorry about this. Hindi ko alam, laging pag may klase saka siya sumusumpong. So siguro allergic ako sa mga students. Ano? Hindi, joke lang. Hold on. Okay, so where were we? We're talking about the error estimate. So, problema sa mga methods is we don't know how close our approximates are. Remember our halting criteria. Meron tayong interval-based. Yung nagsasabi gaano tayo kalayo mula sa actual root, which is fine because that gives us the error. Gaano kalayo yung root dun sa approximate natin. That's fine. Okay? Pero nag-work lang siya para sa interval methods. Pero pag pumunta na tayo sa iterative methods, the only stopping criteria that we have are the function-based stopping criterion, which measures how far is your estimate, all right, the function value of your estimate from 0. So gusto natin mo-compare yan with epsilon. Pero hindi niya binibigay yung error, gaano kalayo si x sub n dun sa actual root r. Binibigay niya gaano kalayo yung function value ni xn kay 0. Kasi nga root yung hinahanap natin. So we don't have an idea how close x sub n is to the actual root. The other one is the jump-based criterion, which measures the relative jump between one estimate to another, right? And we compare it to epsilon. Now, hindi niya sinasabi, again, kung gaano kalayo yung yung estimate natin from the actual root. It is telling us may significant pa bang pagbabago dun sa estimate na ibibigay sa akin when I perform another iteration. Alright? So basically, ang mini-measure niya yung pagiging cushy dun sa mga nag-155 na nung, uh, nung sequence of estimates. Gano'n na magkakalapit yung mga estimates dun sa tail end nung sequence of approximates. But this doesn't tell us how far or how close our current estimate is from the actual root. Kasi ang gusto nating makita ay yung value na to. How near is x sub n to r? If you know r, then that's fine. Mako-compute mo yan. Kung alam mo yung actual root, mako-compute mo itong value na to. Pero ang problema nga natin, root finding so hindi natin alam yung eksaktong r because if we know exactly what r is, then there's no point in performing the algorithm, or performing the method, unless you're doing an academic experiment wherein you're looking for yung convergence and so on, tinetest mo lang yung method mo sa isang function na alam mo na yung root. Pero sa practical scenarios, if you're doing a research, hindi mo alam si R. Kaya ka nga naghahanap ng root finding algorithm, at least numerically. Alright? So hindi natin na-estimate gaano kalapit si R kay X sub n. Again, unless you are doing an interval-based method. Okay, now, ang kagandahan sa Newton-Raphson method is a simple analysis and using one of the results na medyo siguro uh, hindi nyo pinapansin or binabrush off nyo lang nung Math 36, makakakita tayo ng estimate para dun sa value na to or dun sa error, the absolute error involved in the approximation. Okay, and I think that is in theorem 3.2, which is the error estimate for the Newton-Raphson method. So hindi to error bound. So sa Math 174, naghahanap tayo ng error bound. No? So yung error bound, pag sinabi nating error bound, yun na yung pinakamalaking posibleng error, right? Because the theorems that we have for error bounds ay mukhang ganito yung itsura. Okay, less than some value, let's call it m. An error bound will tell us that the error will not exceed a certain number m. Pero kakaiba tong sa Newton-Raphson method, I want to emphasize it. It's an error estimate. This will tell us approximately how far is the root from the estimate that we got. Hindi siya error bound, pero ini-estimate niya gaano kaliit yung error. Kasi yung mga error bounds, pag nagbigay ka lang ng malaking value ni m, pwede mo nang sabihin siya ay error bound. Okay, kasi alam mo na yung error ay hindi lalampas doon. But you might encounter a very pessimistic bound na napakalaki ni M na sure ka na hindi nalalampas. Maganda sana kung tight yung bound. Ibig sabihin, maliit yung value ni M, so alam mo kung saang neighborhood o saang ballpark pumapatak yung absolute error. Yun yung problema sa error bounds, okay? So actually, it's another theme in researches in numerical analysis in finding a tight bound. Gusto natin mas tight o mas maliit yung error bound para mapaliit natin yung or magkaroon tayo ng mas magandang idea how accurate the error is. Okay? Kasi sabi ko nga kanina, palakihin mo lang si M, sure ka yung inequality ay mag-hold. Pero we want to get the smallest possible M to get a better idea of how good our estimate is. Okay? Dito sa Newton-Raphson method, yung theorem 3.2 is a gem of a result because it tells us approximately how far is our estimate from the actual solution. Okay? So hindi siya error bound, isa siyang estimation. Okay? So hindi siya less than, pero approximately nandun siya sa neighborhood na yan. Okay? Now, so ibig sabihin, magkakaroon tayo ng isang magandang idea kung gaano katama or kung gaano na kalapit or kalayo yung estimate natin dun sa actual root. Okay? And this theorem has a very simple assumption. So you just have a function f that is twice continuous over the interval ab containing a root of f. Okay? And then if the root doesn't make the derivative vanish at zero, which is our usual assumption kasi nga pag ang f prime of r ay nag-equal kay zero, baka hindi mag-converge yung Newton-Raphson approximation kasi numerically, if f prime is very close to zero, then the denominator in our iteration will be close to zero. And sometimes if you have computer with a small memory, laging iti-treat niya na zero yung denominator, hindi na magpo-proceed yung iteration. Okay? So that's the usual assumption for the Newton-Raphson method. And it says that for n greater than 0, especially for large n's, ang distance between r and x sub n is the difference between x sub n plus 1 minus x sub n. Meaning, para malaman kung gaano kalayo yung yung current estimate natin dun sa actual value na hinahanap natin, computein mo pa yung susunod na iteration, which is madali lang naman kasi x sub n plus 1 is equal to x sub n minus f of x sub n all over f prime of x sub n. Okay? Tapos, isubtract mo doon yung current estimate mo. Okay? And that will give an idea how good the estimate x sub n is. So, i-run mo lang siya ng isa pang beses para mahanap yung error estimate. So this gives me another idea na kanina ko lang na-realize na pwede pa pala tayong magbigay ng isang stopping criterion para kay Newton-Raphson. Kasi nga, nami-measure natin yung estimate ng error. So pwede tayong magkaroon ng isang, say, tawagin natin siyang error estimate-based stopping criterion. Ito naman yung i-measure natin. Sabihin ko, gusto ko yung yung estimate ko ay within 10 to the minus 8 ng actual root. So to check if I am really within 10 to the minus 8 of the actual root, I will just compare x sub n plus 1 with x sub n and see if the difference is around 10 to the minus 8. Okay? So, napaka-powerful ng result na to. Kasi nga, kahit hindi natin alam si R, okay, na-estimate natin yung error doon sa approximation na nakuha natin. And it's not hard to compute it because it's just running the algorithm one more time and then subtracting from it the current estimate that we have. Okay? So I want you guys to think about theorem 3.2 a little bit, ponder on it, because I might give a problem related to this in the problem set. Okay, medyo may naisip ako magandang tanong para sa problem set involving this one. Okay? Okay, so let's try to prove it. Though nilagay ko siyang exercise 3.2, yung proof ng theorem na to. Pero sige, I'll write the proof and then I think you will prove the one for the secant method. Pwede niyo siyang pag-isipan. Okay. Now, okay, so ngayon tingnan natin kung paano natin to makukuha. All right? So now, here we are assuming r is the root of f. Okay? So ibig sabihin, pwede kong isulat si f of x sub n to be equal to f of x sub n. So I'll sketch the proof. Kayo na lang yung magdagdag ng details. All right? So yung mga details sasabihin ko na lang verbally and then you'll be the ones to write it. Okay? So this is f of x sub n equals f of x sub n plus f of r. All right. And then I can do this because r is a root of f. So that means f of r is equal to 0. Okay. Or gusto ko ba minus? Yeah. I think I want a minus here. Okay. So nothing fancy there. It's just a clever trick. Alam ko ang f of r ay 0. So pwede ko siyang isubtract from f of x sub n. And this equation is true, right? And then I'll use the mean value theorem. By the mean value theorem, okay, since f is continuous and it is differentiable, all right? Hindi nga lang differentiable si f kasi yung f prime continuous din. Yun yung ibig sabihin ng C2. Si f at saka si f prime ay parehas continuous. So f is automatically differentiable by that notion, okay? So by the MVT, there exists a number, C sub n, around x sub n. Okay. All right. Actually, I can be more particular about it, and I can say C sub n between r and x sub n, such that ang derivative ng x sub n ay equals sa f of x sub n minus f of r all over x sub n minus r. Hold on. nawala si C. Di pala siya f of x sub n. Ito ay C sub n. Alright? So, ito yung mean value theorem. Sabi ng mean value theorem, may nag-exist na C sub n sa pagitan ni R at saka ni x sub n such that the derivative evaluated at that number C sub n is equal to this guy, which is basically the slope of the secant line passing through x equals x sub n and x equals R. Okay? Tapos, note that this guy looks like this, all right? Tawagin natin itong equation star, and then this double star. So I can use a variant of double star. I can multiply both sides by x sub n minus r. Lagay ko siya dito, okay? And then I'll delete this guy. So here I'm seeing that f of x sub n minus f of r can be written as x sub n minus r all over f prime of c sub n. So that means equation star becomes f of x sub n equals x sub n minus r times f prime of c sub n. Okay? And then, ano yung pwede kong gawing susunod? Hold on guys, ito na naman siya. Okay, sorry about that again. So yeah, so everything so far, everything good so far. So let's see, ano yung pwede kong gawin yan? So I can divide both sides by f prime. Okay, so okay, divide ko lang both sides. I'll get this. Okay, and then if x sub n is close enough to c sub n, all right. So ibig sabihin, sorry, if x sub n is close enough to r, okay. So pag malapit na si r kay x sub n, so ibig sabihin si c sub n ay palapit na ng palapit kay x sub n. Alright? Kasi 'di ba si c sub n ay between, sulat na pala siya dito. Okay. Si c sub n ay nasa pagitan ni r at saka ni x sub n. But remember, if the Newton-Raphson method will converge, then r will be very, very close to x sub n. Eh, si c sub n, isang number sa pagitan nilang dalawa. So, ibig sabihin, pag super lapit na ni r kay x sub n, yung c sub n ay approximately equal na kay x sub n. So, that means I can replace this by x sub n. Okay? And then, what can we say about this guy? This guy actually comes from the Newton-Raphson iteration. Remember that x sub n plus 1 ay equal kay x sub n minus f of x sub n over f prime of x sub n. Ito yung Newton-Raphson formula. And then I can play with this. Equation and have f of x sub n all over f prime of x sub n is equal to x sub n minus x sub n plus 1. All right. So the ratio between the value of f and f prime at the number x sub n is x sub n minus x sub n plus 1. So this guy can be written as that. Pwede ko siyang isulat as x sub n minus x sub n plus 1. And then I'll just multiply both sides by a negative 1 and then use the symmetry of equality. And I'll obtain r minus x sub n equals x sub n plus 1 minus x sub n as desired. Okay, so here we have proven na yung distance between our nth estimate and the actual value r is approximately equal to, approximate na lang pala yan, sa x sub n plus 1 minus x sub n. It became an approximation because, saan nga siya naging approximation? Kasi nga pinalitan natin si c sub n ng x sub n. Alright? So this guy was replaced by x sub n earlier. So dapat pala dito palang approximately na yung sinulat ko. Okay? Dito, equality pa yan kasi C sub n pa yung ginamit ko. But starting at the point where I change C sub n to X sub n, naging approximation na lang yung mga equal signs. All right? So, is that clear, guys? Sorry, medyo bothered talaga ako nung allergy ko ngayon. So, kung ano nang minsan napapagsabi-sabi ko. Alright, but I hope that's clear. Kung medyo magulo, balikan nyo na lang yung recording, alright? Feeling ko kung ano-ano na mga nasabi ko pa ulit-ulit ako. But anyway, any questions so far? Okay. So kung wala na, or dinedelaying tactics nyo lang ako. Hindi kayo sumasagot para magtagal. Hindi ko masimulan yung secant method. Wala kayong exer sa Monday. Alright, so I hope hindi ganun. Alam ko yan kasi tactic din namin yan nung undergrad. Alright. Pinapakwento namin si prof ng kung ano-anong mga bagay para hindi matapos yung topic. Walang exer sa Monday. Alright, or walang quiz the next day. But I think that's enough of the Newton-Raphson method. Okay, it's a fast method. However, there's a problem. Again, the problem is kapag ka malapit tayo sa isang relative maximum or relative minimum. Kasi dun sa mga points na yun, nagzi-zero yung first derivative. So hindi tayo makaka-proceed dun sa Newton-Raphson iteration. Or even if f prime of x sub n is not exactly zero, if it is very, very close to zero, how close depende dun sa machine precision. If your computer or if your programming application only handles say 6 significant digits or 8 significant digits, kapag ka yung f prime of x sub n ay of order 10 to the minus 7 or 10 to the minus 8 na, your computer will treat it as a zero. So mag-division by zero error na, hindi na mag-proceed yung iteration. So that's one problem of the Newton-Raphson. Okay? At saka yung isa pa niyang problema, hindi tayo sure na lagi siya nagko-converge. We need to use x of 0 that is close enough to the actual root. Okay? Now, some of these disadvantages are addressed by the next method that we'll be talking about. Ito naman yung secant method. And as the name implies, secant line yung gagamitin natin. So isa rin tong straight line method katulad nung Newton-Raphson. So kumukuha tayo ng isang straight line that will approximate the behavior of the curve, alright? And then kukunin natin yung x-intercept ng line na yon as our estimate for the root. And we will do this as long as our stopping criteria are not met. Okay? Actually, itong secant method ay halos kamukha ng regular falsy. Kasi di ba sa regular falsy, ginagawa natin, meron tayong interval, kinukuha natin yung line passing through the endpoints of the curve. Tapos kinukuha natin yung x-intercept nun. So secant method, ganun din yung idea, kaya lang wala tayong interval na kinoconsider dito. Instead of an interval, we are using technically two initial conditions, x sub 0 and x sub 1. So if you look at figure 3.5, we're trying to get the root r of the blue curve, y equals f of x, right? And then we'll start with two initial guesses, x sub 0 and x sub 1. So dalawa yung initial condition. Then we'll take the point passing through those two x values, right? The line passing through the points generated by those x values. So this is f of x1, f of x sub 0. Let's take the line, joining them. And then the x-intercept of that line is basically our x sub 2, our next estimate. Okay. Now, the theory behind the secant method is very related to the Newton-Raphson method, because remember this, you can treat this as a secant line, and as your x sub 0 becomes closer and closer to x sub 1, then the slope of the secant line is very, very close to the derivative, right? Remember, dyan ang galing yung notion ng derivative. You take the limit of f of x plus h minus f of x all over h as h approaches 0. Basically, this is, the ratio in the limit is the slope of the secant line. Pag kinuha mo yung limit as h approaches 0, or when the distance between those two x values that you used is very, very close to 0, you'll get the slope of the tangent line. So ganun din yung idea. So nangyayari rito ay lumiliit yung distance between two consecutive estimates. And then as they become closer and closer to each other, the secant lines that you generate will have slopes that are very, very close to the derivative of f, which is basically ano yung nangyayari sa Newton-Raphson method. Okay? So kung ipapagpatuloy niyo yung iteration, so meron tayong x sub 2 rito. Alright, let's see. Kukunin ko yung f of x sub 2. Ito siya. And then I'll take the line passing through x sub 2, f of x sub 2, and x sub 1, comma f of x sub 1. So ito yung line passing through those 2 points. Okay. Tapos yung x-intercept na yon, yun yung magiging x sub 3. Okay? And then ulitin ko yung process. And if you will also draw the tangent line here, yung tangent line sa pagitan ni x1 at saka ni x2 ay medyo kamahawig na nung slope ng tangent line. Alright? Kasi nga malapit na si x1 at saka kay x2. So basically, that's the secant method. Ang pinagkaiba niya sa Newton-Raphson, dalawa yung initial condition. Tapos para mag-iterate ka as if you are doing the regular falsy method. Kasi nga kukunin mo yung line passing through those 2 points, which in the regular falsy method, siya yung endpoints ng interval, right? Tapos kinukuha mo yung x sub 2. Pero rito, wala tayong interval na kinoconsider. Hindi nyo kailangan mamili kung ano yung susunod na mga points na gagamitin nyo sa susunod na iteration. It is always the last 2 points. Okay? Now, paano siya analytically madiderive, or how can you write the algorithm for this method? Well, analytically, it's easy because remember in kamukhang-kamukha nga siya ng Newton-Raphson, no? So pwede niyong kunin, pwede niyong gawin yung same analysis that we did before na kunin yung equation ng line passing through x sub n, comma f of x sub n, at saka x sub n minus 1, comma f of x sub n minus 1, and do the same manipulation as what we did with the Newton-Raphson method. And then you will arrive with a formula for x sub n plus 1 using x sub n and x sub n minus 1. Okay? Or pwede naman mag-take advantage tayo dun sa makihitch tayo dun sa nakuha natin mula sa Newton-Raphson. Remember, sa Newton-Raphson method ay ito yung nakuha nating formula. Alright? Kaya lang ngayon, ano ba yung nire-represent ng f prime? Yung f prime of x sub n, ang nire-represent niya yung slope ng tangent line passing through x sub n. Pero remember, we are not looking for the x-intercept of the tangent line, but of the secant line obtained by using 2 previous estimates. Alright? So, ibig sabihin, ang mangyayari lang dito, yung slope na to, papalitan ko lang nung slope ng line passing through x sub n and the previous point, x sub n minus 1. So basically, yung slope na yan mapapalitan kasi nga hindi tangent line yung ginagamit natin, yung secant line yung ginagamit natin. So this will become f of x sub n minus f of x sub n minus 1. So that's your change in y all over change in x. Okay, and that's it. That's the formula for the secant method. All right, or you can transfer this and put it in here. Tawag na lang, hindi na siya kasha. Pero algebraic manipulation na lang naman yon. Ito na siya. Okay. So you will get this. Medyo nagpalit lang ako ng indexing. Okay. So ito yung slope nung line passing through 2 previous points para makuha yung x sub n. So basically, if you kept your Newton-Raphson code from last time, pwede niyong palitan yung papalitan niyo lang yung pagko-compute ng x sub n. Instead ng gamitin niyo ay f prime, papalitan niyo lang siya nung slope nung tangent, yung slope ng secant line. Alright? So yun lang talaga yung papalitan nyo mula dun sa Newton-Raphson method. Okay? Because here again, the recommended stopping criterion is a jump-based stopping criterion. Okay? Any questions? Clear ba yung method? Can I see some reactions? Or wala na kayo nakukuha ngayon sa lecture? Feeling ko talaga sabog na sabog ako today. But hopefully you get the idea. Eh, ba't wala nag-reply? Walang nagre-react. Sige, hirapan ko yung susunod na exercise. Okay, no worries, Charles. But I hope I'm making a little bit of sense. All right, so ganun yung method. All right, ganun yung secant method. Now, let's see a quick example. All right. Example 3.3. Inulit ko lang yung ginawa natin sa example 3.1. Kukunin ko yung largest root ng x to the 6 minus x minus 1 using a jump-based stopping criterion with epsilon equals 10 to the minus 6. And then I will use this initial conditions. Okay, I think I'm back. Baka na-disconnect ako for some time there. And as I was saying na-disconnect ako, biglang na-disconnect ako ulit. Sorry about that. Again. Okay, tapos naputol na naman. Kaya siguro hindi ko nakikita yung mga reactions nyo. I am having crappy internet connection again today. Okay, so in figure 3.6, you will see my implementation of the secant method. And okay, finally, nag-update din siya. Sorry about those 5 minutes na on and off ang connection ko. All right. So in figure 3.6, you will see my implementation of the secant method for the problem of finding the largest root of x to the 6 minus x minus 1, which is basically the same function that we dealt with starting with module number 2, and an implementation of the required 7 iterations bago ko ma-meet yung stopping criterion. Okay? Now, if we recall, dun sa Newton-Raphson, okay, ilan ngang iterations yung kailangan? Sa Newton-Raphson method, I only needed 6 iterations para ma-meet yung stopping criterion. It took me how many? It took me 7 iterations, so one more iteration than the Newton-Raphson method. And though this is not comparing apples with apples, all right? Hindi parehas yung comparison kasi yung Newton-Raphson, isa lang yung starting condition, all right? So hindi natin ma-adapt yung same initial condition for the Newton-Raphson with the secant method to give us a fair comparison. Kasi pag gusto niyo, pag magko-compare kayo ng bilis ng isang method, dapat parehas yung starting conditions para masabi niyo na you're comparing apples with apples and oranges with oranges, right? Hindi natin yung magagawa with the secant and the Newton-Raphson method kasi sa secant method, dalawa dapat yung estimates o yung initial conditions. So, but essentially, you will realize na mukhang mas mabilis talaga yung Newton-Raphson. Kasi pwede nating tingnan yung secant method as an approximation of the Newton-Raphson method. Kasi nga, yung slope na ginagamit natin sa secant method is basically an approximation of the derivative. Dun sa derivative na ginagamit natin sa Newton-Raphson, assume na natin na yung second point na ginagamit natin ay super lapit dun sa actual x sub n. Pero dito sa secant method, yung second point, which is x sub n minus 1, ay gusto pa nating palapitin ng palapitin kay x sub n. So bago maging masyadong malapit na malapit yung x sub n saka yung x sub n minus 1, kailangan natin ng maraming iterations. So n is large enough so that the slope of the secant line is approximately equal to the slope of the tangent line. So kaya you can imagine na mas mabilis talaga yung Newton-Raphson kaysa kay secant method. And true enough, okay, ang rate of convergence ng secant method is just around 1.618, which is a golden ratio 1 plus square root of 5 all over 2. So remember, ang rate of convergence ng Newton-Raphson ay 2. Si secant method, around 1.618, faster than the bisection method, faster than the Regula-Falsy method with the Illinois algorithm, sila ay 1.442. Pero itong secant method, mas mabilis ng konti dun sa Illinois Regula-Falsy kasi ito ay 1.618, but it falls behind the Newton-Raphson method. Now, ano yung advantage ng secant method? Well, hindi tayo masyadong concerned about relative extrema. All right? Na nagzi-zero yung second derivative. And then, ano pa ba? Well, sa number of operations, mas tipid din yung secant method. Kasi pag nag-i-implement ka ng Newton-Raphson method, at every step of the way, you need to calculate two function values. You need to calculate f of x sub n and f prime of x sub n. And usually, the nonlinear functions that we're dealing with are complicated. So yung pagko-compute mo ng f of x sub n might require some more work for your computer. Okay? Tapos, kung komplikado si f, so most likely, mas komplikado rin si f prime. Okay? And you need to evaluate x sub n or you need to evaluate f prime at x sub n. So in terms of function evaluation, medyo magastos yung Newton-Raphson. So kung ita-time mo siya, yung actual running time ng algorithm ay medyo matagal kasi nga at every step of the way, you are dealing with two calculations. Now, you might also say na, sir, sa secant method, dalawa rin naman yung function evaluation na nangyayari. We need to calculate f of x sub n and f of x sub n minus 1. Okay? Yung function value sa dalawang previous estimates. Or kung susundin natin yung formula doon kay notes, f of x sub n minus 1 at saka f of x sub n minus 2. Right? So sir, paano ka makakatipid ng function value evaluations about iteration? Well, if the derivative of f prime is much more complicated than f, then calculating f of x sub n minus 2 is a nice trade-off for calculating f prime. Okay? So isa yun. Pero you can also write your secant method so that hindi mo na kailangan computein yung f of x sub n every time. Para sa bawat iteration, isa lang yung bagong function value na kinocompute mo. Kasi remember, given na tayo ng x0 at saka x1, so they are already given. Okay? So, pwede mong computein si f of x sub 0 at saka si f of x sub 1. Okay? Tapos, sa pagko-compute mo ng f of x sub 2, actually, sabihin natin f of x sub 3, alright? Kailangan natin yung x2 minus f of x2 times x2 minus x1 all over f of x2 minus f of x1. All right? However, dun sa pagko-compute natin para kay x2, na-compute na natin yung f of x1. So pwede na lang nating i-save yung function value mula dun sa previous estimate. Para sa halimbawa, pagko-compute kay f of x sub 3, pwedeng nakastore na yung value ni f of x1 na ginamit natin to compute f of x2. So we can reduce the work done in every iteration of the secant method by just saving the function value for the point 2 steps back. All right? Kaya pwedeng maging isang function evaluation na lang yung secant method, just recalling something from memory rather than computing two function evaluations, all right, or performing two function value evaluations, which would have been the case for a very naive implementation of the secant method, all right, which I guess is much more efficient than the Newton-Raphson method na kailangan pang computein yung f prime, and there is no way to save time on that. Okay? So yun yung mga bentahe ng secant method. Kaya nga dun sa exercise gusto ko sana ipa-compare yung time spent running the algorithm, okay? Running the Newton-Raphson and the secant method. Kasi nga ang idea, I was thinking na number of iterations wise, mas county lang yung number of iterations na kailangan sa Newton-Raphson kasi nga quadratic yung rate of convergence niya. Etong secant method, golden ratio lang, 1.618. Pero to perform each of the iterations, mas maraming trabaho yung kailangan gawin ng computer dun sa Newton-Raphson. Kailangan yung computein si f of x sub n at saka si f prime of x sub n. Kay secant method, I can write it in a nice way so that at every step of the way, isa lang yung kino-compute niya. Okay? Kaya lang medyo fail kahit dun sa answer key na ginawa ko. Yung program ko kasi ay nagpa-plot din kasi gusto ko makita yung animation nung estimates, alright? So, kaya medyo matagal. Inabot ako ng 1 or 2 seconds for the Newton-Raphson method. Tapos, essentially, naging mas mabilis pa rin yung Newton-Raphson. Kasi nga, halos magkadikit lang yung number of iterations needed for both of them, pero hindi ganun kakomplikado yung f prime para dun sa problem natin, dun sa exercise. So yeah, but if you will be dealing with much more complicated f's that will yield even more complicated f primes, then probably sacrificing around 0.4 from the rate of convergence could be more efficient. All right, um, if you are concerned with the number of the number of operations done per iteration. So mukhang okay yung trade-off na i-give up ko yung 0.4 sa rate of convergence from the Newton-Raphson down to the secant method, pero mas madali kasi baka mas madaling i-implement yung secant method than the Newton-Raphson method. Okay? So those are the pros and cons of this method, advantage of one over the other. So I hope you see the idea about them. Just a closing remark for the secant method. Well, the nice thing about the secant method, because it is really very related to the Newton-Raphson method, yung error estimate para dun sa secant method ay kaparehas din nung sa Newton-Raphson. So, nagbago lang ako dito ng index, pero the error at the n-1 iteration is approximately equal to the difference between the estimates from the nth and the n-1 iteration. Okay? So, yun. All right, so I think we can stop here. Sorry for the interruptions, either due to my allergy or to my crappy internet connection today. Hopefully, nakabalik ako to explain some of the things. And then most of the things, kung medyo sabog yung discussion ko today, I apologize. But you can read most of them dun sa module, all right? So, nandun rin naman sila. Okay, and then on Friday, we'll be talking about fixed point iterations. And depending on how far we can finish or we can tackle on section C of this module, then we can adjust the laboratory exercise 1.2 part B accordingly. Okay? So, any questions? Okay, wala bang questions? I hope meron kahit konting nag-come across na message today. Kahit yes, super bothered talaga ako ng allergy ko. Ang hirap magpigil ng hatching, no? So I know you know it also, guys. So yon. Other concerns? Okay, so if there are none, so please stay safe and ano pa ba? Ayan, nawala yung ending spiel ko. No? So, I hope you guys enjoy the rest of the day. And until Friday, stay safe and let's see each other again by then. Okay, bye everyone.
Thank you po, sir.
Thank you po.